Hello students, today we will discuss about carrier generation and carrier recombination. What is this process and how it plays a role in changing the conductivity of a semiconductor. In our previous lectures, what we have seen that the semiconductor behaves like an insulator at absolute zero temperature, and as the temperature increases, the conductivity of the semiconductor increases and it starts behaving like a conductor. Let us see what is happening when temperature increases. When temperature increases, some of the electrons they get energy and they become excited, and due to which some of the bonds breaks over here. Like here if you see, this bond is breaking due to the gain in energy, and when a bond breaks, the electron which was bound to this silicon atom that becomes free from the atom, and it is known as a free electron. When the electron becomes free from its space, it leaves behind an empty space. Here this is the empty space, and those empty spaces are known as holes. So the electron which is moving from the atom, that is known as free electron, and the empty space left by the electron is known as hole. Looking into the band diagram, here what we have seen, there is no carrier movement, or the electron cannot move from the valence band to conduction band due to this forbidden energy gap. When the electron will move, once the electron gains an energy which is either equal to Eg or more than Eg, then the electron will move from the valence band to conduction band. Once the electron gains an energy equal to or more than Eg, it will move from valence band to conduction band. Similarly, if this electron gains an energy which is equal to or more than Eg, it moves to conduction band. Similarly, the third one I have shown over here. So whenever an electron gains an energy equal to or more than Eg, it moves to conduction band. This process that an electron is moving from the valence band to conduction band, what is left behind? There is an empty space which is known as hole. So whenever the electron moves from valence band to conduction band, we are getting one electron in the conduction band. At the same time, it is leaving behind a hole in the valence band. And this electron and this hole together, they are known as electron-hole pair. They are created in pair. An electron cannot move without creating a hole in the valence band. They are created by pair. That's what they are known as electron-hole pair. So generation is the process through which an electron-hole pair are created. Electron moves from valence band to conduction band, and because of which we are getting an electron-hole pair. The electron gain energy. How the electron is moving from valence band to conduction band? Because it is getting some extra energy, that may be from light energy, thermal energy, or some radiations. Whenever it is getting some extra energy which is either equal to Eg or more than Eg, it will move to conduction band. That means electrons are gaining energy. Breaking of covalent bond. As I showed you in the previous slide, whenever the electron is getting an extra amount of energy, there is a breaking of covalent bond, because of which we are getting this electron-hole pairs. The electrons transit from valence band to conduction band. Here you can see the number of electrons moving from the valence band to conduction band is same as the number of holes created in the valence band. If one electron is moving, then it will leave behind one single empty space, and that is a single hole. If two electrons are moving, we will get two empty spaces in the valence band. That means the number of electrons moving to the conduction band is equals to the number of holes created in the valence band, and that is if we are denoting N as the number of electrons moving to the conduction band, P is the whole concentration, then N is equals to P is equals to Ni. Ni is nothing but our intrinsic carrier concentration that we will be discussing in more detail in further lectures. We have seen that in generation we are getting an electron hole pair being generated. Now what is carrier recombination? What is the difference between this generation and recombination? We all know that the electrons, they always try to be at the minimum energy state. So when they are getting excited to the conduction band, they always try to come back to the stable state, that is the minimum energy state. And during this process, when an electron is coming from that conduction band to valence band, what is happening? This electron over here is missing, and again this hole is also missing. They are getting eliminated. So this is the process of recombination through which electrons and holes are eliminated. Because the electron, whatever they are in the conduction band, it is coming down and it combines with an hole over here in the valence band. That means one electron from the conduction band is eliminating, and we are also getting one hole being eliminated from the valence band. Similarly, if this electron is moving from conduction band, it will eliminate one more hole from the valence band. During this process, when the electron is coming from a higher energy level to a lower energy level, because it is coming from conduction band to valence band, the extra amount of energy that is lost by the electrons. So electrons are losing energy. Further, what we have seen, the electrons are moving from conduction band to valence band. That means that the transition of electrons takes place from conduction band to valence band. Rebreathing of ruptured covalent bond. In the previous case, that is during the carrier generation, we have seen that the covalent bond is breaking, and due to the breaking of the covalent bond, we are getting the electron hole pair. And here, as the electron is coming and getting recombined with the hole, that broken bond is getting rebreathed. So the transition from the conduction band to the valence band, that may be direct or indirect, that we will see further. The recombination can be of three different types. The first one is direct or band to band recombination. Second one is with trapping, and third one is agar recombination. What is the difference between these three? Direct to or band to band recombination occurs when the electron comes directly from the conduction band to the valence band, and the extra amount of energy is released either in form of photon or some radiations. That is known as direct recombination. Then the second one is, it may occur with a trapping. Instead of coming directly from the conduction band to the valence band, it will stay for some time in an intermediate level which lies between the conduction band and valence band, and that is known as with trapping. So the electron transition occurs by an extra energy level in the forbidden gap. The third type is agar recombination, that involves a third carrier. Like if it is moving in the conduction band, it will transfer its energy to some other electron, and as it is transferring some of its energy, the electron energy will reduce and it will come back to the valence band. That is, the agar recombination involves three carriers. Recombining electron transfers its energy to another electron in the conduction band. Let us understand these three types of recombination with the following diagram. Here, in this diagram, this green one represents the valence band, this yellow one is the conduction band, and these red dots over here are electrons. Generally, these electrons, they will try to come back to the valence band, but there are different ways through which they can come back to the valence band. We will see one by one. In the first case, this electron is coming directly to the valence band. It is not stopping in between. So this direct transition from the conduction band to the valence band is known as direct or band to band recombination. It is coming from the conduction band to the valence band directly and getting recombined with a hole over there. In the second type of recombination, what is happening? The electron, while it is taking the transition from the conduction band to the valence band, it will being trapped by an extra energy level which is present in between the conduction band and valence band. Here, if this is the extra energy level, while this electron is coming to the valence band, it will stay for some time in this energy level. So this will stay for some time and then it will come back to the valence band. This is known as the recombination with trapping. Coming to the third type of recombinations, this electron, while it is in the conduction band, there itself it will give its energy to another electron. Here it is giving its energy to this electron, and after giving the energy of this first electron will reduce and hence it will come back to the valence band, and these types of recombinations is known as Agar recombinations. These are the three different types of recombinations occurs in case of some semiconductors. Now we will see the mathematical derivations for recombination and generation. Generally at thermal equilibrium or steady state, what happens? The number of electrons, the number of holes, that remains constant. That means the carrier concentration is maintained. Now if we take the generation rate, that is the number of electron hole pairs created per unit volume per unit time, that is noted as GI, and recombination rate, that is the number of electron hole pairs eliminated per unit volume per unit time, that is Ri. Then Ri is equals to GI, because the carrier concentration should be maintained. That means there should not increase or decrease in carrier concentration, that is either hole concentration or electron concentration. That means if four numbers of electron hole pairs are being generated, there should be four recombination as well to maintain the number of holes and number of electrons. That's what Ri is equals to GI. Ri is the recombination rate and GI is generation rate. This generation rate and recombination rate, they are temperature dependent. If we are increasing the temperature, we know that many numbers of bonds will break and number of carriers will increase. That will increase the number of electron hole pairs. That means this generation and recombination rate are temperature dependent. They are proportional to equilibrium concentration of electrons as well as they are proportional to equilibrium concentration of holes. If I am taking the recombination rate as Ri, then this is proportional to N0. What is N0 over here? That is the equilibrium concentration of electron. Similarly, Ri is also proportional to equilibrium concentration of hole, that is denoted as P0. Combining these two, I can write Ri is proportional to N0, P0. And if you remove the proportionality sign, then Ri is equals to some proportionality constant alpha R N0 P0. Here you should know that N0 P0 is equals to Ni square. What is N0? N0 is the electron concentration, P0 is our hole concentration. That the product of N0 and P0 is equals to Ni square. What is Ni over here? That is the intrinsic carrier concentration. Using this over here, here it is N0P0. In place of N0P0, if I will substitute Ni square, what will you get? We will get Ri is equals to alpha R Ni square, and this is also equals to the generation rate. Ri is the recombination rate, Gi is generation rate, and generally I told at thermal equilibrium or steady state, the carrier concentration is maintained. That means the generation rate should be equals to recombination rate, and hence Ri is equals to Gi is equals to alpha R Ni square. Further, this alpha R depends on the mechanism of recombinations. How the recombination is occurring, what are the energy associated with that. For generation, like to give the extra energy to the electron, what are the form of energy, either it is thermal energy or light energy, what is the form of energy associated for this generation or recombination process. Depending on that, this value of alpha R changes. Today we have seen what is the process of generation and recombination, and they occur simultaneously at steady state to maintain the carrier concentration. We will study about the details of carrier concentration in our further lectures. Till that, go through these modules and don't forget to like, subscribe and share my channel. Thank you all and have a nice day. Bye.